Have you ever just felt like completely overwhelmed with information? Like you're trying to learn something new, but it just feels like a jumbled mess of facts and figures?
Oh, yeah, definitely. I think we've all been there. It's like
Mhm.
you're drowning in information overload, and
Yeah.
you just wish there was some way to cut through the noise.
Exactly. You just want that aha moment where it all clicks and you see the bigger picture.
Right, you want to see how it all fits together without getting bogged down in all the little details.
Well, that's what we're going to try to do today. We're going to take a deep dive into the idea of a generalized knowledge graph, or GKG,
It's a pretty fascinating concept.
and potentially a really powerful tool for making sense of all this information that's constantly bombarding us.
Definitely, especially in today's world where everything seems so interconnected.
All right, so let's start with the basics. What exactly is a generalized knowledge graph?
Well, at its core, it's all about representing knowledge as a network. Instead of just listing facts, a GKG organizes information in a way that shows the relationships between different concepts.
Okay, so instead of just having a list of random facts, we're talking about a more structured approach.
Right, think of it like a map. The key pieces of information are like cities on the map, and the relationships between them are the roads that connect those cities.
That's a great analogy. So then what makes it generalized?
What makes it generalized is that it brings together three different types of these knowledge maps. You have your standard knowledge graphs, or KGs, which focus on relationships in the physical world. Then there are event knowledge graphs, or EKGs, which, as you might guess, are all about how events unfold and relate to each other. And finally, you have common sense knowledge graphs, or CKGs, which try to capture our general understanding of how things work, the kind of knowledge that we often take for granted.
Okay, so we have these three distinct but interconnected types of knowledge graphs. Let's break those down a little bit more, starting with the basic knowledge graph. What exactly is a KG designed to capture?
A knowledge graph is really good at representing factual relationships between things in the real world. Like, for example, Lincoln, born in 1809.
Okay, so that's a pretty straightforward example. Lincoln and 1809 are the entities, and born in is the relationship that connects them.
Exactly. It's about capturing those very concrete and static relationships.
Got it. So KGs are all about the who, the what, and the basic connections between them. But then event knowledge graphs sound like they add a whole other layer of complexity.
Yeah, EKGs bring time and sequence into the picture. So instead of just saying Lincoln was born in 1809 and Lincoln died in 1865, which is what a KG might do, an EKG would actually represent those as separate events and then link them with a temporal relationship, like Lincoln born in 1809 before Lincoln died in 1865.
So EKGs are not just about what happened, but when it happened and what happened next.
Precisely. It's about capturing the dynamics of events, how they unfold, and how they relate to each other.
That makes sense. And then we have these common sense knowledge graphs, which sound even more abstract.
Yeah, CKGs are all about capturing the kind of knowledge that we don't always explicitly state, but that we all kind of inherently understand. Like the fact that we're born before Roe died.
Okay, so that's a very general statement that applies to pretty much any living thing. It's not about a specific person or a specific event.
Exactly. CKGs are about those general patterns and relationships that underpin our common sense understanding of the world.
Interesting. So KGs are the what, EKGs are the when, and the then what, and CKGs are like the why, the underlying rules of the game.
That's a good way to put it.
And what's interesting is that even though these three types of knowledge graphs seem quite different, they all share this basic element structure.
Right, that common structure is really important. It suggests that there might be some underlying connections between these different types of knowledge.
Which makes you wonder why we've traditionally approached building them in such separate ways.
Exactly. Historically, there have been different methods, different data sets, and even largely separate research communities focusing on each type of graph.
And that just seems inherently inefficient.
It requires a lot of duplicated effort. And what's really intriguing is that the knowledge contained in one type of graph can actually be incredibly valuable for building the others.
Right. It's like having three different teams trying to solve related problems, but they're not allowed to talk to each other.
Exactly. And when you do start to share that knowledge, you can see some really impressive results. Like, for example, there was a study mentioned in the source material where they used hierarchical KGs to improve the extraction of biomedical events from text.
Oh, yeah. I remember that they were able to get much more accurate results by leveraging the information that was already encoded in the KG.
Right. And there was another example where they used KGs to enhance a language model called BERT, which then led to better performance on medical text classification.
So by combining these different types of knowledge, they were actually able to improve the overall understanding of the medical domain.
Precisely. It shows the potential of a more unified approach.
And that brings us to the work that we're diving into today, this new framework called GKG-LLM.
Yeah, this is where things get really exciting.
So tell us, what's the big idea behind GKG-LLM? What are they trying to achieve?
The core innovation of GKG-LLM is to build all three types of knowledge graphs, KG, EKG, and CKG, together within a single integrated framework.
Okay, so it's all about breaking down those silos and creating a more holistic approach to knowledge representation.
Exactly. And the potential benefits are pretty significant. By learning shared patterns across all three graph types, the model can become much more efficient, and it can leverage knowledge gained from one type to improve its performance on the others.
It sounds great in theory, but I imagine there must be some pretty serious challenges in actually making this work.
Oh, absolutely. And one of the biggest challenges is what they call task-specific differences.
Right, you mentioned that earlier. Can you explain what makes it so difficult to unify the construction of these different types of graphs?
Even though they all share that basic element relation element structure, the actual tasks involved in building them are quite diverse.
Can you give us some concrete examples?
Sure. Just within the realm of knowledge graph construction, you have things like sentence-level relation extraction, where you're trying to identify the relationship between two entities within a single sentence.
Okay, so that's pretty focused.
Right. But then you also have document-level relation extraction, where you need to understand how entities are connected across multiple paragraphs or even an entire document.
So the scope of the task gets much broader.
Exactly. And then there's joint entity and relation extraction, where
Yeah.
you're trying to identify both the entities and their relationships simultaneously.
Okay, so that sounds even more challenging. And those are just the tasks for building KGs. What about EKGs?
EKGs come with their own set of challenges. You have sentence-level event detection, where you first need to determine if a sentence is even describing an event. Then there's document-level argument extraction, where you're piecing together all the key information about an event from different parts of a document. And then you have event temporal relation extraction, which is all about figuring out the timeline of events, what happened before, what caused what, and so on.
Wow, so we're going from very localized tasks within a single sentence to tasks that require understanding an entire document, and then to tasks that involve reasoning about the relationships between events.
And then when you get to common sense knowledge graphs, you encounter yet another set of tasks. Things like abstract generation, where you're trying to distill the underlying common sense from a piece of text and language inference, where you're trying to figure out the logical implications of statements based on our general world knowledge.
So you've got this whole spectrum of tasks ranging from very specific to very abstract, from sentence level to document level and everything in between.
Exactly. And that's what makes it so challenging to come up with a unified approach that can handle all of these different demands.
So how does GKG-LLM actually address this challenge? What's their secret weapon?
The key ingredient is the use of large language models, or LLMs, like GPT-4 and LaMDA3.
Those incredibly powerful language models that everyone's been talking about.
Right. And what makes LLMs so well suited for this task is that they have a very standardized input-output format. They essentially operate in a sequence-to-sequence manner,
Meaning
you can feed them a sequence of text or data, and they can produce another sequence of text or data as output. And this uniformity allows us to reframe all those diverse knowledge graph construction tasks into a consistent format that the LLM can understand and process.
So it's like the LLM acts as a universal translator, taking in different kinds of data and instructions and outputting structured knowledge in a consistent way.
That's a great way to think about it.
But just having a powerful LLM isn't enough, is it? You still need to train it effectively to perform all of these different tasks. And that's where this three-stage curriculum learning approach comes in.
Exactly. They don't just throw all the data at the LLM at once. They break the training process down into 3 distinct stages, each building upon the previous one.
Okay, so tell us about these stages. What happens in stage 1?
Stage 1 is called KG empowerment. And the goal here is to inject foundational knowledge from standard knowledge graph datasets into the LLM. They start with a base LLM and then fine-tune it on a variety of KG datasets.
So it's like laying the groundwork, teaching the LLM the basic building blocks of knowledge.
Right. It's all about entities and the relationships between them. They use a standard cross-entropy loss function during this stage,
Right.
which basically means the model is learning to predict the correct relationships between entities.
So it's learning to distinguish between correct and incorrect connections.
Exactly. And by the end of this stage, they have what they call the G-micro model, which has this basic understanding of entities and their relationships.
Okay, so G micro is the foundation. What happens in stage 2?
Stage 2 is called EKG enhancement. And as you might guess, it's all about event knowledge graphs.
So now the LLM is learning to deal with those more dynamic and time-based relationships.
Right. It's moving beyond just static facts to understanding how events unfold and how they relate to each other.
And they use EKG datasets for this stage.
Exactly. They fine-tune the G-micro model on a variety of EKG datasets. And the goal is to produce what they call the G-mid model.
Which is now capable of understanding both simple relationships and event sequences.
Precisely.
And then finally we have stage 3.
Stage 3 is called CKG generalization, and this is where they bring in the common sense knowledge graph data sets.
So now the LLM is moving into the realm of more abstract and general knowledge.
Right, it's learning to capture those underlying patterns that govern our common sense understanding of the world.
And the output of this stage is the final GKG-LLM.
Exactly. And what's really interesting about this stage is that they also include some countertask data.
Countertask data. What's that?
It's basically data that's designed to prevent the model from becoming too specialized.
Oh, so it's like giving the LLM a broader perspective, preventing it from getting stuck in a rut.
Exactly. And the countertask data they use is called WebNLG, which is a data set focused on generating text from structured data. So it's kind of the opposite of what they're doing with knowledge graph construction.
Interesting. So by including this countertask data, they're forcing the LLM to think more flexibly and to generalize its knowledge to a wider range of situations.
Precisely.
Okay, so we've got this 3-stage training process that takes the LLM from basic knowledge of entities and relationships to understanding event sequences and finally to grasping more abstract common sense knowledge. It's like a carefully crafted curriculum for an AI student.
Yeah, it's a really elegant approach. And the researchers argue that this staged approach makes sense because there's a natural progression from KGs to EKGs to CKGs.
Right. The simple connections in KGs can be seen as the building blocks for the more complex event structures in EKGs. And understanding those event structures is a step towards capturing the even more abstract patterns in CKGs.
Exactly. There's an inherent relationship between these different types of knowledge.
Now, to train an LLM, effectively, you need a ton of data.
Oh, yeah, definitely. And they really went all out on the data collection for this research.
They mentioned something like 15 subtasks across 29 different data sets?
Yeah, it was a massive effort. They ended up with around 806,000 training examples and another 140,000 for testing.
Wow, that's a lot of data.
It is. And they carefully categorized this data into 3 groups. In-sample data, which is the standard data used for training and evaluating each specific task, counter-task data, which we already talked about, and then out of distribution, or O data.
O data, what's that?
O data is data that the model has never seen during training. It's used specifically to test how well the model can generalize to new and unexpected situations.
Ah, so it's like the ultimate test. Can the model apply what it's learned to something completely new?
Exactly.
And with all this data coming from so many different sources, how did they manage to feed it into the LLM in a consistent way?
They standardized the format of all the data into a unified structure with 5 key elements: an ID, an instruction, a few-shot, zero-shot indicator, the input, and the output.
Okay, so break that down for us.
Sure. The ID is just a unique identifier for each data point. The instruction tells the LLM exactly what task it needs to perform. The few-shot, zero-shot indicator specifies whether the LLM will be given a few examples to learn from or if it has to figure it out on its own. The input is the actual data that the LLM needs to process, and the output is the expected result.
So they basically created a standardized template for all the data.
Right. And to make the training even more robust, they actually used another LLM GPT-4 to generate different ways of phrasing the instructions for each task.
So they weren't just relying on a single way of describing each task. They wanted to make sure the LLM could handle different variations.
Exactly. And for some of the tasks, they also included a few example input-output pairs to give the LLM a bit of a head start.
Interesting. So it's like they're providing the LLM with both a clear set of instructions and a little bit of guidance.
Exactly.
Now, when you're dealing with these massive LLMs, one of the big challenges is the computational cost of training them. They mention using a technique called LoRa Plus to address this. What is LoRa Plus, and why was it so important for this research?
LoRa Plus, which stands for Low Rank Adaptation Plus, is a very clever technique for fine-tuning large language models in a much more efficient way,
Efficient in terms of?
in terms of both time and computational resources. Instead of updating all the billions of parameters in the LLM LoRaWAP Plus only adjusts a small subset of
Okay,
them.
how does it do that?
It uses something called low-rank matrix approximations, which is a way of simplifying complex systems. Imagine you have a giant control panel with thousands of dials, and each dial represents a parameter in the LLM. Instead of trying to adjust every single dial, LoRaWAP Plus figures out which dials have the biggest impact and focuses on tuning just those few key
When
dials.
it's like finding the levers that matter most and ignoring the rest.
Exactly. And this makes the fine-tuning process much faster and less computationally intensive.
Which is crucial when you're dealing with LLMs of this scale.
Absolutely. And LoRa Plus actually improves upon the original LoRa method by allowing for more flexible adjustments to those key parameters, which helps the model learn more effectively and converge to a good solution more quickly.
So it's all about efficiency and making the most of the available resources.
All right, Leslie.
Okay, so they've got their massive data set, they've got their standardized data format, they've got their powerful LLM, and they've got their efficient fine-tuning technique. Now, the big question is, did it actually work? Did GKG-LLM deliver on its promise?
The results were really impressive. They compared GKG-LLM to a bunch of other state-of-the-art models, including both closed-source models like GPT-4 and open-source models like LAM-A2 and LAM-A3. And across all 15 knowledge graph construction tasks and all 29 datasets, GKG-LLM consistently outperformed the competition.
Wow, that's a pretty strong statement. Can you give us some specific examples of just how much better it performed?
Sure. In the knowledge graph tasks, GKG-LLM achieved an average improvement of over 12% compared to the best closed-source LLMs.
12%. That's a huge margin.
It is. And even when they compared it to a baseline model that was specifically trained on just knowledge graph data,
Right.
GKG-LLM still showed an improvement of over 7.5%. It was consistently either the best or the second best model across all the KG tasks.
That's amazing. And what about the event knowledge graph tasks?
For EKGs, GKG-LLM again achieved the best overall performance with a minimum improvement of almost 10% over the closed-source LLMs. And what's really interesting is that it also performed really well on those challenging Odoo datasets, the ones that had never seen before.
So it wasn't just memorizing patterns from the training data. It was actually learning something more fundamental about how events work.
Right. It was able to generalize its knowledge to completely new situations. And on those OD datasets, it significantly outperformed the next best model.
Wow, that's really impressive. And finally, how did it do on the common sense knowledge graph tasks?
For CKGs, GKG-LLM again showed very strong results, consistently ranking among the top performers. There was one specific OD text classification task where GPT-4 edged it out, but GKG-LLM still came in second.
Interesting. So even on these more abstract tasks, it was holding its own against some of the most powerful language models out there.
Exactly. And overall, across all the CKG tasks, GKG-LLM showed an average improvement of almost 7.5% over the strongest baseline model.
Those are some seriously impressive results. It really does seem like this three-stage curriculum learning approach, combined with the efficient LoRa plus fine-tuning, was a winning combination.
Yeah, definitely. And they also did some really interesting experiments to investigate different aspects of their approach.
Like what?
Well, for example, they did what are called ablation studies, where they systematically removed or changed certain parts of their approach to see how it impacted performance.
Okay, so it's like trying to isolate the key ingredients that contributed to this success.
Exactly. And one of the things they looked at was the impact of using diverse instructions versus just a single instruction for each task. And they found that having a variety of instructions actually led to significant improvements in performance.
So it's like giving the LLM multiple perspectives on the same problem, which helps it to learn more effectively.
Right. And they also looked at the impact of including a few example shots in the prompts versus relying solely on zero-shot learning. And again, they found that including those few shots led to significant performance gains.
So even though these LLMs are incredibly powerful, they still benefit from a little bit of hand-holding sometimes.
Definitely. And then they took it a step further and removed both the diverse instructions and the few-shot examples.
And what happened?
The performance dropped quite a bit, which really highlights the importance of those data preparation and prompting techniques.
Interesting. So they really went the extra mile to make sure the LLM had everything it needed to succeed.
They did. And those ODE results are also really telling.
How so?
The fact that GKG-LLM performed so well on those unseen datasets suggests that it wasn't just memorizing patterns from the training data. It was actually learning something more general and more transferable about how knowledge is structured and connected.
Right. It was able to adapt to new situations and solve problems it had never encountered before. Yeah,
Exactly. And that kind of generalization is really what we're ultimately aiming for in AI.
absolutely. They also did some analysis on the impact of the amount of training data they used, didn't they?
They did. They trained the model using different proportions of the full data set, ranging from just 10% up to 100%.
And what did they find?
They found that, as you might expect, the performance generally improved as they used more data. But they also noticed that there was a point of diminishing returns. After about 80% of the data, the performance gains started to level off.
So there's a sweet spot in terms of data efficiency.
Exactly. And they also investigated those LoRa plus hyperparameters, the learning rates for those key parameters that we talked about earlier.
And what did they learn there?
They found that the model's performance was actually quite sensitive to these hyperparameter settings, but they were able to find an optimal range of values that yielded the best results.
So even with these efficient fine-tuning techniques, there's still a bit of an art to getting the best performance.
Definitely.
And finally, they did those stage generalization experiments. What were those all about?
The stage generalization experiments were designed to test whether the earlier stages of training actually benefit the later stages. So they took those intermediate models, G micro and G mid, and tested them on tasks from the subsequent stages.
And what did they find?
They found that there were some trade-offs, as you might expect. But overall, the results supported the idea that there's a real connection between those different stages of training,
Including.
meaning that learning the basics of KGs in stage 1 actually helped the model to learn EKGs in stage 2, and learning EKGs in stage 2 helped the model to learn CKGs in stage 3.
So the knowledge gained in each stage was transferable to the later stages.
Exactly. And it also confirmed that the order they chose for the training KG to EKG to CKG was the most effective.
Because there's that natural progression from the simpler to the more complex, from the concrete to the abstract.
Right. And they even showed that this three-stage approach was better than simply training the model on all the data at once.
Interesting. So it's not just about the data, it's also about how you structure the training process.
Exactly.
So this has been a fascinating deep dive. It really seems like GKG-LLM is a significant step forward in our quest to build more unified, more efficient, and ultimately more capable knowledge representations.
I completely agree.
And it really makes you think about the bigger picture, doesn't it? If we can develop these more sophisticated ways of representing and understanding knowledge, what kind of impact could that have on areas like AI or how we search for and use information?
Oh, the possibilities are really endless.
Could it even change the way we think and learn as humans? Could it lead to new discoveries and breakthroughs that we can't even imagine yet?
It's definitely possible. And the researchers are already exploring the application of GKG-LLM in domains like intelligent healthcare, which has the potential to revolutionize the way we diagnose and treat diseases.
That's really exciting. So much potential for positive impact.
Definitely.
Well, that's all the time we have for today, but I encourage everyone to check out the show notes for links to the source material and some other resources that you might find interesting. Thanks for joining us on this deep dive, and we'll see you next time.
Thanks for having me.